Okay, so in our last section, we covered linear growth, which recall, if we were to graph it, graphs as a straight line. Exponential growth, however, is what we're going to cover here. And we tend to have a lot of situations where exponential growth occurs. Exponential growth occurs in any population, in how fast rabbits grow, in how fast the population of people grows. Those are exponential growth problems. And a good example of exponential growth is the growth of a disease like COVID-19. So I found a very nice, perfect exponential graph for coronavirus cases in India. Now, they don't always turn out to be this pretty and this perfect, but this is what an exponential function looks like when we graph it. And this is, of course, cumulative cases. So exponential functions have a tendency to look like they're almost level to begin with. But then as we go onward, the growth goes very, very, very fast. And notice this graph of India's coronavirus cases, that growth is occurring very, very quickly at this point. And of course, this is as of September 18th. So very quick growth as it gets into this part of the curve. So an exponential curve looks quite different than a linear curve. And at first it rises much more slowly than a linear curve, but then it rises much more quickly than a linear growth problem. Sorry, my dog is deciding that she's got to say hello in the background. So let's take a look at this exponential growth problem. A population of a small town is 1,000. If the town grows by 3% each year, find its population after 20 years. Okay, now we are going to we're going to actually come up with an exponential growth formula from this problem that we can use in future problems. And you won't have to do what I'm about to do with every problem. But let's remember, as we were doing linear growth, we had P sub 0 was always the initial amount. All right, so here the initial amount, or the initial population of this town is 1,000. All right, well, let's calculate how many people will be in this town after 1 year, okay, or P sub 1. Okay, now let's think about this. There's going to be the original 1,000 people, but then there's going to be 3% more. And let's remember, when doing percentages, to get 3% more, we would take 3% as a decimal, 0.03, and multiply it times 1,000. All right, so really, if we put that into the calculator, 1,000 plus 0.0 times 1,000, we're going to get 1,030 people in this town now. Okay, now I want to kind of highlight that because we're going to come back to that number. Okay, but I want us to get used to a little bit of the idea of the formula here, and I'm going to put that down below. All right, so let's notice that this 1,000 was our P sub 0. So I'm going to replace the 1,000 with the symbols for the 1,000 with P sub 0. So actually, I think I can just copy and paste this. So 1,000 is really P sub 0. And same thing, oops. Same thing right here, 0.03 times 1,000. The 1,000 was really P sub 0 again. So I'm going to put P sub 0 instead of the 1,000. Now, remember from algebra, if we have really P sub 0 by itself is really 1 P sub 0. And in algebra, if we had two like terms like x and x, we could add the numbers in front of them. So same thing is true here. I can add 1 plus 0.03, and I will get 1.03 P sub 0. All right, now, I think you will agree that if I do this little trick, I think you'll agree that 1.03 is equal to 1 plus 0.03. Okay, so I just wrote that out in front of my p sub 0. We're going to come back to this idea to help us with our formula. All right, let's go to the second year. How big is our population going to be in our second year? P sub 2. All right, so let's think about what we would do. We would take the prior year, which the population of at the end of year 1 was 1030, and we would multiply 0.03, 3% of our 1030 times that 1030, and that would tell us how much we're going to have after year 2. So we're taking the population that we currently have at the end of year 1 and adding 3% more. So 3% times 1030. All right, so let's let our calculator do that. And if we do, we end up with, there are now 1,060.9 people. Now, of course, we're never going to have a 0.9, but for the sake of numerical values, we'll go ahead and write that 0.9. We'd probably round this up to 1,061 people. All right, but I want to kind of highlight that. Okay, so let's just symbolize what we've got here. All right, so I want you to notice, all right, 1,030 was the answer to P sub 1, and that answer is the same thing as this right here. Okay, so I am going to copy this in place of 1030. All right, so let's do that. Copy this in place of 1030. And then also, right here, I have 0.03 times 1030. So I'm going to, again, copy what I just had instead of the 1030. Okay, so this is kind of weird looking, but in algebra, we can do something else. We can do something called factoring. And when we factor, we can take out anything that we have in common in two terms. And really, this whole thing is a term, and this whole thing is a term. An addition sign actually breaks up terms. All right, and notice that they have in common this 1 plus 0.03. They both have that set of parentheses, that 1 plus 0.03. So I'm going to factor it out. And when I factor it out, think of it as I'm yanking that entire set of parentheses, 1.03, to the front. And when I yank it out, I am left with a P sub 0 right here. And actually, I'll copy and paste it so I don't have to keep. I'm left with that P sub 0 right there. And I'm left with a 0.03 right here and this P sub 0 when I yank out those parentheses. So I'm left with 0.03 P sub 0. All right, now that I've got this stuff right here, I want you to notice that P sub 0 plus 0.0 P sub 0 is exactly the same thing I had back here, and I changed that into this. So I'm going to change this into this. So let's notice what we've got. 1 plus 0.03 times 1 plus 0.03 P sub 0. Okay. All right, so let's do this one more time just so we can see the trend. And it's okay if you're having trouble understanding this procedure. I do want to show you where this formula is coming from, but we will, actually, let's go ahead and do it from now. I think you can see the trend from here. So let's notice that this thing was 1 plus 0.03 to the first times p sub 0. This is really 1 plus 0.03. Notice there's two of them. So to the second times p sub 0. As we get to p sub 3, it will be 1 plus 0.03 multiplied 3 times p sub 0. So keeping that in mind, let's write an nth formula. Our nth formula, p sub n, I can't get that thing to turn off. There we go. We are going to multiply 1 plus 0.03 n times, so that's really the nth power. Notice this was 2 times for p sub 2. It would have been 3 times for p sub 3. So really it's the power, the number of times that we're multiplying it, and then times p sub 0. Okay, with that in mind, let's answer this question. We want to find its population after 20 years. All right, so we want to find p sub 20. Well, we are going to replace our n with 20 in the formula. Well, it does not want to do this. So notice I've replaced the n with a 20, and I've replaced p sub 0 with what p sub 0 was, 1,000. Now, we're going to work this out in our calculator, but I want you to be careful. I want you to do this a step at a time. So if we do order of operations, parentheses come first. So let's do the 1 plus 0.03 first. 1.03, and we still have it to the 20th power. And then it's times 1,000. And remember that if we just have a number by itself in parentheses, that's really multiplication, and the parentheses are just separating it from the previous number here. Okay, so now exponents are next in our order of operations. So let's do 1.03 to the 20th power in our calculator. Now, depending on your calculator, if you have just a small calculator, you should have a button that says x to the y power on it or y to the x power. That is your exponent. Or you might have a caret, a little caret symbol that is your exponent. So when I raise 1.03 to the 20th power, I get 1.806111. And now lastly, let's multiply it by 1,000. And that will be 1,806.1111. Now, generally, since we're talking about a population here, we're probably just going to round this to the whole number. There'll be approximately 1,806 people at the end of 20 years. Not very much in such a small town.